Hi, my name is Kelly Mitchell. I am a PhD candidate with Dr. Jeffrey Firkins at The Ohio State University, and today I'll be discussing the stimulation of microbial protein synthesis by branched-chain volatile fatty acids in dual flow cultures varying in forage and corn oil concentrations. Branched-chain volatile fatty acids are formed by the degradation of branched-chain amino acids. This process is shown here on the right, with leucine being broken down to isovalerate, isoleucine being broken down to 2-methylbutyrate, and valine being broken down to isobutyrate. Now, some bacteria, cellulotics in particular, are not able to perform this process themselves, and they rely on branched-chain volatile fatty acids to synthesize their own branched-chain amino acids since they cannot break down branched-chain amino acids or uptake them, and they cannot make branched-chain amino acids from pyruvate. Branched-chain volatile fatty acids can be used for branched-chain long-chain fatty acid synthesis. Again, cellulotics in particular were known for their high proportion of branched-chain long-chain fatty acid in their membrane structure. They use these branched-chain long-chain fatty acids to maintain membrane homeostasis and fluidity in different room and environments. Shown on the right here, we can see that both isovalerate and isobutyrate are elongated into iso long-chain fatty acids. However, isovalerate forms odd chain, while isobutyrate forms even chain. 2-methylbutyrate is unique in that it forms anti-iso long-chain fatty acids, and odd chain ones is that. Previous research with branched-chain VFA supplementation has shown benefits for cellulitic bacteria in particular because of their need for branched-chain VFA for synthesis of branched-chain long-chain fatty acids and branched-chain amino acids. They've seen improvement in NDF degradation in addition to increased microbial protein synthesis, which would benefit dairy cattle in today's environment by increasing feed efficiency and increasing the supply of microbial protein going to the small intestine. Though there has been previous branched-chain VFA supplementation research performed, literature is still limited in branched-chain VFA usage, especially isovalerate and 2-methylbutyrate, since those branched-chain VFAs co-elute on most gas chromatography setups. Therefore, the objective of the study was to determine what dietary conditions increase branched-chain VFA usage. To determine this, we had a 2x2x2 factorial arrangement of treatments where the first factor was a high forage or low forage diet, where we expected a high forage diet to increase cellulitic bacteria population, therefore increasing branched-chain VFA usage. Our second factor was either no supplemental fat or supplemental fat dosed as corn oil for a polyunsaturated fatty acid or PUFA dose. We expected PUFA to decrease branched-chain VFA usage due to the bacteriostatic effect of PUFA on cellulitic bacteria. And our final factor was either no supplemental branched-chain VFA or an additional 2.15 millimoles per day of each branched-chain VFA. This dose was determined to double the concentration of branched-chain VFA in the vessel, and we expected that to increase branched-chain VFA usage since there was more branched-chain VFA available for the bacteria that utilized it. On this slide, we have a more detailed breakdown of the diets provided to the fermenters. The forage was coming from an alfalfa pellet, but the majority of it came from this orchard grass pellet. And then the concentrate was a concentrate pellet that was formulated for each of the 4 diets. We maximized NDF in the high forage diets while minimizing it in the low forage diet, and then minimized starch in the high forage diets while maximizing starch in the low forage diet. Across all the diets, though, we did maintain the crude protein to be at 15%. The reason that we performed this experiment in dual flow continuous cultures is we were able to maintain the pH to minimize diet differences, even though we were feeding a very high forage diet versus a very low forage diet to these fermenters. So across all these diets, pHs were maintained to remain the same, so that we were looking at branched-chain VFA usage with dietary conditions changing and not with the pH additional effect changing. Shown here are a couple of pictures of our dual flow continuous cultures, the one on the left being empty so you can see the agitation mechanism, and the one on the right showing them actively running during this research project. Now, in these fermenters, we're able to control temperature, pH, and passage rate, so that we were looking at branched-chain VFA usage without any other confounding effects. Shown here is a typical period design for a fermenter study. In this case, we had 4 total periods. It begins on day 0 with inoculation. There's adaptation, background sampling before isotope dosing, and isotope dosing, where we dose 15N to determine the efficiency of microbial protein synthesis, as well as 13 carbon from the branched chain VFA dose to determine branched chain VFA usage. On the last 4 days of the study, we collected effluent, and from that effluent, we took a VFA sample to determine VFA production. We dried an effluent sample to determine NDF degradation or nutrient degradation overall. And then we also took a bacteria pellet to determine efficiency of microbial protein synthesis. Then the data that I'm going to show you today was analyzed using the mixed procedure of SAS, where we had the random effective period, the random effective vessel, or each individual fermenter, and then the fixed effect of forage, corn oil, and branched chain VFA dose, and then those fixed effects interactions. For this first table, we have the results of nutrient degradation as well as the efficiency of microbial protein synthesis. In this first row, I am showing the NDF degradation for all 8 treatments. Our results did have an effect where branched chain volatile fatty acids increased NDF degradation by 2.97 percentage units, but corn oil also increased NDF degradation by 6.46 percentage units, but only in the low forage diet. Now, this was unexpected since corn oil should have a bacteriostatic effect on cellulitic populations, but we did have a very controlled pH environment where our pH ranged between 6.1 to 6.8, so our cellulitics weren't very stressed. Therefore, this PUFA dose didn't have a bacteriostatic effect that we expected. In this second row, we have rumen degradable protein in our 4 different diets. We did have a difference in RDP where the low forage diet had greater RDP compared to the high forage diet. I'm going to continue to discuss this in this next slide. But since branched chain volatile fatty acid supply does come from branched chain amino acid supply, we expect with higher RDP that there was more branched chain volatile fatty acids in those vessels. But corn oil did increase RDP in the low forage diet as well. So we're going to take that into account when we discuss our next slide of data. These last 2 rows are showing measurements of the efficiency of microbial protein synthesis. This third row is showing bacterial nitrogen grams per kilogram of truly degraded organic matter, and branched chain volatile fatty acid did increase this by 1.54 grams of bacterial nitrogen. Low forage decreased this by 1.84 grams. In our final row, we have the bacterial nitrogen grams per gram of truly degraded nitrogen, and branched chain volatile fatty acid did increase this by 0.05 grams of bacterial nitrogen. On this slide, we are showing the net branched chain volatile fatty acid production. Now, from that effluent that I discussed in our methods slide, I did a volatile fatty acid sample, so I could determine total branched chain volatile fatty acid production. Net production means that I subtracted out the branched chain volatile fatty acids that we did dose. So those are shown here where the high forage is in the blue, high forage plus branched chain volatile fatty acid is in the diagonal stripes, and then high forage plus corn oil is shown with the dark border, and high forage with corn oil plus branched chain volatile fatty acids is shown with the dark border as well as the diagonal stripes. Low forage is the same pattern except in yellow. So the pattern here goes high forage with branched chain VFA, high forage with corn oil, high forage with corn oil and branched chain volatile fatty acids, low forage and branched chain VFA, low forage and corn oil, low forage and branched chain VFA and corn oil. Across all of these, we had a significant interaction of diet and branched chain volatile fatty acids, where branched chain did decrease the net production of branched chain volatile fatty acid. Therefore, saying if we supplied it, they did use it. But we also had a decrease in branched chain volatile fatty acids in the high forage compared to the low forage. Now, we did have a higher RDP in the low forage diet. Therefore, we would have expected a higher supply of branched chain volatile fatty acids and a higher net production of branched chain VFAs. So directly comparing these for branched chain VFA usage is difficult to do, but we did see a difference in high and low forage, and we did see a decrease in net branched chain VFA production with branched chain VFA supplementation. And then on this final slide, I am showing the 13 carbon recovery in the bacteria pellets for the high forage and low forage diet with or without corn oil. Since we only dose 13 carbon with the branched chain VFA treatment, there's no control treatment for this. We were looking at the total 13 carbon recovery. But for this analysis, we did run this statistics with a branched chain VFA net production as the covariate. Since we did have that difference in RDP, we wanted to account for that between the high and low forage diet. So that's what that covariate's purpose was. However, even with that covariate in the model, we still had an increase in our total dose recovered with the high forage diet. So that increased our dose recovery by 4.93%, which does mean in the high forage diet, they were using more of our branched chain VFA dosed. Our results did show that supplementing branched chain VFA did improve microbial efficiency as well as NDF degradation. So this would improve feed efficiency in dairy cattle. The forage to concentrate ratio and branched chain VFA supplementation both affected net branched chain VFA production, but there were differences amongst the RDPs in the two different diets that were going to influence these changes. The higher forage diet did increase 13 carbon dose recovery in the bacteria pellet, so the branched chain VFA that we supplied in that diet was utilized more compared to the low forage diet, but there was no effect on corn oil on branched chain volatile fatty acid utilization. In the future, we're going to be looking at the amino acid profile of the diets, effluent, and bacteria pellets so we can determine how the branched chain amino acid profile and the RDP differences change branched chain VFA availability in our different diets. Additionally, the 13 carbon label will be traced into the branched chain aldehydes, the branched chain long chain fatty acids, and branched chain amino acids to determine under these different diets, did microbes utilize the branched chain VFA more for branched chain amino acids, branched chain long chain fatty acids, or where was that 13 carbon ending up? Thank you very much for listening. If you have any further questions, my email is posted right here. I'd be happy to answer any of them.